In this module, we can discuss the output SNR for optimum filter receiver. In the last module, we have discussed the calibration of the probability of error expression. Let us take the same probability of error expression. That is P is equal to half ERMC of x01 of t minus x02 of t by 2 root 2 sigma. So irrespective of the positive level or negative level of inputs, we obtain the probability of error expression as shown here. Now, so in order to reduce the probability of error, you have to maximize the SNR. That is, you have to maximize the square of the output SNR. Let us assume that square of output SNR as some rho. So you have to maximize this rho max to minimize the probability of error, where rho max is x naught of t whole square by sigma square, where x naught of t is a change in the output signal level, that is x01 of t minus x02 of t. Now, for this, let us let at t is equal to capital T at one particular instant, let us assume that the Fourier transform of x of t be x of f. We know that x of t is x1 of t minus x2 of t, where x1 of t is a positive level of input and x2 of t is a negative level of input. And similarly, let us assume x0 of t as x01 of t minus x02 of t by t, and let that Fourier transform of the output signal be x0 of f. Then you can define the output signal in frequency domain as the product of transfer function and the input signal in frequency domain, because transfer function is defined as a ratio of output signal to that of input signal magnitude in frequency domain. So you can write x0 of f as h of f into x of f. So you can represent x0 of t as now integral of, just you are applying the inverse Fourier transform to the above signal. So you will get x0 of t, which can be written as integral minus infinite to plus infinite x0 of f into e power j omega t df, where x0 of f, let us substitute this x0 of f as h of f into x of f into e power j omega t df. So now you are well familiar with the numerator term in the rho max, that is x0 of t. What is x0 of t now? Integral minus infinite to plus infinite h of f into x of f into e power j omega t df. Let us focus on the denominator section. That is, variance sigma square can be written as expectation of n naught of t whole square minus mean square. But mean is 0 here. So sigma square can be written as expectation of n naught of t whole square, which is nothing but the integration of its output noise PST, where output noise PST is nothing but the product of square of transfer function and input noise PST. So now you are familiar with x naught of t whole square and sigma square. Now we are going to write rho max in terms of the output signal, where rho max is the square of output SNR. So in order to prove that, evaluate that, you should be familiar with the Schwarz inequality. It states that the square of magnitude of integration of the product of two functions, if the magnitude is always less than or equal to the products of square of integration of the two terms individually. That is, the overall product is magnitude is less than or equal to the individual products. So in order to write in the form of Schwarz inequality, we are assuming theta 1 of f as h of f into root SNI of f. And we are assuming theta 2 of f as x of f into root SNI of f e power j omega t. Because rho max is change in the square of output SNR. So in the numerator, you should get x naught of, in the x naught of t or x naught of f by x naught of f whole square by sigma square you should get. So for that, what you are doing, you are just multiplying with theta 1 of f and theta 2 of f in the numerator. So in order to represent clearly, so rho can be written as integral minus infinite to plus infinite theta 1 of f into theta 2 of f into df whole square. So if you multiply these two expressions, you will get in the numerator as h of f into x of f into e power j omega t. And denominator is theta 1 of f square. If you square this, you can write it as sorry, if you square this theta 1 of f, you can write it as h of f square into SNI of f df. That is nothing but our variance. So that's why what you know the rho as we have expressed in the form of Schwarz inequality, but this whole factor will be less than or equal to their individual products. So we have rewritten this as less than or equal to integral minus infinite to plus infinite theta 1 of f square df into integral minus infinite to plus infinite theta 2 of f square df. Here theta 1 of f square and theta 1 of square gets cancelled, and you will get the rho max, that is square of output SNR, as less than or equal to integral minus infinite to plus infinite theta 2 of f square df. Please substitute theta 2 of f square. So then it will be x of f square by SNI of f, root SNI of f whole square. That will be SNI of f into e power j omega t whole square. The magnitude of e power j omega t is nothing but cos x plus j sin x. The magnitude of square of that will be 1, because cos square x plus j sin square x. Cos square x plus sin square x, the magnitude will be 1. So rewriting this as 1, the square of output SNR rho max can be obtained as uh, equal to integral minus infinite to plus infinite x of f square by SNI of f df. This is rho, and maximum will be equal to this term, that is integral minus infinite to plus infinite x of f square by SNI of f df. So this is the output SNR expression for optimum filter. Here this Schwarz inequality is valid only when theta 1 of f is equal to k into theta 2 star of f, where theta 2 star represents the complex conjugate. So just represent theta 1 of f, which is h of f into root SNI of f, and theta 2 star of f will be x of minus f into root SNI of f into e power minus j omega t. So just rewriting this expression to get the h of f, take this root SNI of f to the RHS. So you will get k into x of minus f into SNI of f into e power minus j omega t. So this expression represents the transfer function of optimum filter. So in this module, we learned the output SNR and transfer function calculation of optimum filter. Thank you for listening. In the next module, we can continue with the probability of error and optimum filter calculation. Probability of error, as well as in the next module, we can continue with the probability of error as well as the output SNR for matched filter. Thank you for listening.